A filter is basically a gain dependent on the frequency. So it can be represented with a transfer function like this. These are the most common used filters. So these are Bode plots. It's easy to explain filters with Bode plots because on the y-axis here we have the gain in decibel. So 0 is 1 and minus 60 is basically 0 and 20 is almost infinity or a really large number. And the x-axis is the frequency. So this Bode plot tells us what gain each frequency has. So as you see, the low frequencies has 1 gain and the high frequencies has 0 gain, which means that we filter out all of the high frequencies. And this time here, this frequency here is the cutoff frequency, and it decides what frequencies we are filtering. And this is the transfer function. Here we have the high pass filter. It looks pretty same as the low pass filter, but we're filtering out the low frequencies instead of the high. And here we have the band pass, where we're filtering out the frequencies below and above a specific area. So we just want the frequencies in the middle. And a band stop is kind of like the reverse, where we're filtering out a specific range of frequencies. We are not going to look at the bandstop filter because it's a bit complicated and it's not the most common filter. So we're going to focus on these three. So as you may have recognized, you can see that if you multiply the low pass filter with the high pass filter, you get a band pass. This is here, if you look at the transfer functions. So there are many ways to make these types of filters, but here we have an example of a low pass filter and a high pass filter. So these are passive, which means that they don't have any op-amps, and passive filters are often more simple than active filters. Now we want to find the transfer function of the low pass filter. We have that the total resistance here, so in series, or the impedance I mean, so total is equal to R plus 1 over SC. And this is the reactance of the capacitor. And the impedance of the output, which is this one, is 1 over SC, right? So this circuit is just a voltage divider, which means that we can write it as V out is equal to ZZ over the total impedance multiplied by VI, right? So now we can write VO over VI as 1 over SC and R plus 1 over SC. Now you can see that we can multiply by S and divide by R in the numerator and the denominator. So we get that 1 over RC and then S plus 1 over RC. And 1 over RC is a frequency, which is the cutoff frequency. So we have omega C and then S plus omega C. This is the same, we can also write it as TS plus 1, where T is the time or the period of the cutoff frequency. And then this is the characteristic for the low pass filter as we saw earlier. And we can do the same for the high pass filter. So then we would still have that VO is equal to Z, and now it's R because they have switched places, right? Over the total impedance, which is the same. and multiply by VI. Almost forgot that. So we can rearrange it, and we get that VO over VI is equal to, now we have R, and then R plus 1 over SC. Then if we divide by R and multiply by S, we get that we have S on top and S on the bottom plus 1 over RC. And this is then equal to S over S plus omega C, which can be written as 1 over T S and then TS plus 1. No. T. Now this is the same as the characteristic for the high pass filter as we saw earlier. So this high pass filter is the characteristic one multiplied by a gain. As we saw earlier, the bandpass was a multiplication of the low pass and the high pass filter in the logarithmic domain. So when we're drawing a circuit, we can just add them together or put them next to each other, right? If you remember, the low pass filter is actually just a multiplication of the low pass and the high pass. So we can just put it next to each other, and then we'd get a bandpass filter. So for this case, we VO over VI is equal to, first, the low pass filter. So we have omega C over S plus omega C. And this is omega C1 because we have two different. And then we multiply by S, or the high pass filter, which is S over S plus omega C2. So this is the bandpass filter. Now, as you see, the bandstop filter is a little bit more complicated, but it's actually basically a low-pass filter in parallel with a high-pass filter. And we also have some other components here as well. So until now, we've been looking at some passive filters, and now we will look at some active filters. So this is the low-pass active filter, and this is the high-pass active filter. You can see that they are a little bit more complicated, and we also have some op-amps. So I just made a video on op-amps, so if you don't understand op-amps, go ahead and look at that. If you want to make an active bandpass filter, you need to set them after each other. So we can just move this one over here. Okay, I need to erase the voltages here. Then we'll just put it after. Yeah, and this is a ground. Like that. And so this will be a bandpass filter.